Welcome to the 16th lecture of this course. Today we will start by giving the formal definition of a context-free grammar and how we formally define acceptance by a context-free grammar. Then we will look at some more examples, and finally we will conclude by showing that the set of regular languages form a subset of the class of languages accepted by context-free grammars. So, definitions and notations. So, a in short CFG is a 4 tuple V is a 4 tuple V sigma PS, where V is a non-empty set of variables. Sigma is the set of terminals. Okay, so let me just underline. So these are the formal terminology. So we have variable, we have terminal. P is a subset of the relation V cross V union sigma star is the set of production rules. Okay, so often these are just called rules instead of saying the whole thing production rules, and S belonging to V is the start variable. Okay, so both these sets V and sigma are finite sets. We will only look at finite sets. V is non-empty because it must contain the start variable, at least it has one variable which is the start variable. Sigma is the set of terminals. As I said last time that we usually denote the variables with capital letters and the terminals with either small letters or numeric symbols. Now this is slightly important. So we have the production rules. So we denote the production rules as a subset of the relations from V to V union sigma star. Okay. So we do not write it as functions from V to V union sigma star. The reason for this is, note that we can have multiple production rules corresponding to one variable. Okay. So for a variable we can even have 0 production rules, or we can have 1 or more than 1 production rules. Okay. So to accommodate for that fact, we have this as a relation instead of a function. So it is a relation from V cross V union sigma star. So one variable gets mapped to a string from which consists of symbols from V and sigma, and the start variable is of course there. So, let A going to W be a production rule, and let U and V be strings in. Okay, so I'll just write it in a shorthand notation. So, U and V are strings over V union So, just one second, I should not write this as a set. So, this is, so V union sigma itself is a set. So, I will just write it with round bracket. So, okay. So, A to W is a production rule, and we have U and V, which are strings over variables and terminal symbols. Okay. Then we say that the string U A V yields U W V in one step. Okay. So, essentially what this means is that if I have a variable in some string, let us say UAV, replacing that variable with one of its production rules gives me a certain string. So, that is what means to say that some string yields some other string in one step. So, now we can generalize this definition. So, for U V in V union sigma star, we say that U yields V if either they are the same strings, okay, or there exists a sequence of strings U0, U1, U2, so on till UK, and U0 equals U, UK equals V, and UI yields, or UI minus 1 yields UI in one step. Okay. So, essentially this is generalizing this to multiple steps. So, we say that a string U yields a string V if basically I can go from U to V in 0 or more steps. So, if U and V are the same, then it means going in 0 steps. Otherwise, I can just have a sequence of strings U0 equal to U, uk equal to v, which are not the same, and I go from u0 to u1 in one step, u1 to u2 in one step, u2 to u3 and so on till uk, each in one step. Okay. So, here we denote this as, so this is denoted as UAV with a double arrow going to UWV. Okay, so, when we have yield in one step, it is indicated with a double arrow, and when we have yield in multiple steps, so this is denoted as U with a star on top. Okay, so, with a star over here going to V. So, this means that from U I can go to V in 0 or more steps. So, now that we have a grammar, okay, let me do one thing, let me just go to the definition of this grammar and give this a name. So, let us call this grammar G. Okay, so, we have this grammar V sigma P S. We define the language of G as, so it is denoted as L of G, and it is the set of all strings W in sigma star consisting only of terminals such that S yields W. Okay. So, all those strings over terminals that we can generate starting from the start symbol. And finally, a language L is said to be a context free language if there exists a, so this is in short denoted as CFL. So, a language L is said to be a context free language if there exists a context free grammar G such that L equals L of G. So, all those languages for which we have a context free grammar are known as context free languages. Okay. So, let us look at some examples. So, the first example that we will see today is let us look at the language L, which has a sequence of A's and followed by a sequence of B's such that n is greater than or equal to 0 and m is greater than or equal to n, but less than or equal to 2n. So, the number of B's is at most twice the number of A's, but more than the number of A's. Okay. So, it lies between n and 2 to the power n. How do we create a language for this? How do we create a grammar for this language? Okay. So, what is the intuition? So, we essentially we want to have we want to form sequence of A's and sequence of B's. Okay. So, we will use the start variable and we will have some variable to form sequence of A's and B's. But when we are forming our sequence of B's, we will use the fact that from one variable I can have multiple production rules, okay, to add either a single B or two B's for every A that I add. Okay. So, let us try to see what we mean. So, we have, let us say we have a production rule going from A to ASB. Okay. So, this capital A will get replaced by a small a. Okay. So, this means that I have equal number of capital A's and equal number of capital B's, or it can go to epsilon as well. And let us say that capital A goes to small a. Now, where do I send capital B to? Okay. So, if I send capital B to, let us say small bb, what I get is for every A I have two B's, which means if I have n number of A's, I will get 2n number of B's. Instead of two B's, if I just keep a single B, then what I get is for every A I have a single B. So, if I have n number of A's, I will get n number of B's only. But what I want is something in between n and 2 to the power 2n. So, what I will do is I will have add two rules B and BB. So, whenever if I have any number between n and 2n, I will use the second production rule to add twice the number of B's, and then when the number of A's becomes equal to the number of B's, I will use the first production rule. Okay. So, this ensures that the number of B's cannot be less than the number of A's, and it cannot be more than twice the number of A's. Okay. So, this is I mean a very important example where we use the fact that I can have multiple production rules for one variable to accept languages which have this kind of a form. So, of course, this is our start variable, and small a and small b are the terminals, and capital A, B and S are the variables. Okay. Now, let us look at another example. So, this is an example of a non-regular language that we had proven earlier. Okay, so we take, let us call this L, so let us call this one L1, so we will call this L2. L2 consists of strings over 0, 1 such that W has or the number of zeros in W is equal to the number of ones in W. So, it has equal number of zeros and ones. So, before proceeding to create a grammar for this language, let us try to understand the intuition. Okay. So, when I look at a string which has an equal number of zeros and ones, firstly I can break up this string, firstly I can divide this into two cases. Either the string starts with a 0 or the string starts with a 1. In either case, suppose the string starts with a 0. If the string starts with a 0, then this starting 0 is matched by some 1 somewhere down in the string. Okay. So, for example, let us say that I have a string W which starts with a 0, then because this string has equal number of zeros and ones, I have this 0, then maybe I have some other string in between, and there is a 1 which gets matched to it. By matched, I mean that this inner portion again has equal number of zeros and ones. And then again there can be something after this also, maybe there is a string after this. So, I can have some string, but the property is that, so for both these pieces, this one as well as this one, so both these parts have an equal number of zeros and ones. Okay. So, this is the case when the string starts with a 0. Even if the string starts with a 1, I have a similar sort of analysis. So, now I want to use this fact to construct a context free grammar. So, I take my start variable and I replace s with 0 followed by s 1 s. Okay. So, this means that I have 0 and 1 which are matching each other. So, this one is basically matching the first 0, and between them I can have any string. So, basically s can get replaced with again some other string which is generating an equal number of zeros and ones, and again after the 1 I can have a string which has an equal number of zeros and ones which s is generating. So, I have this. I also have the case when the string starts with a 1. So, I will have 1 s 0 s, okay, and I have the empty string epsilon, because by definition this string does not have any 0 or 1, which means that it has 0 number of zeros and 0 number of ones which are equal. Okay. So, this is essentially the grammar. So, this grammar has only one variable s, it has 2 terminals and it has 3 production rules. Okay. So, now we will see our third example, which is kind of similar. So, this is known as the language of balanced parenthesis. So, basically balanced parenthesis means is, so balanced parenthesis is a string over, so it has 2 symbols, the left parenthesis and the right parenthesis. Okay. So, it has 2 symbols such that they are balanced and well matched. Okay. I mean, it should not be that. So, balanced means that I should have equal number of left and right, and well matched means that I should have a left before I have its corresponding right. Okay. It should have this thing. Okay. For example, so this is an example of a balanced parenthesis. So, this one gets matched with this one gets matched with this one, and this one gets matched with this one. Similarly, I can have something like okay. So, this one gets matched with this one gets matched with this, and this one gets matched with this. Okay. On the other hand, if I have something like, let us say, this. So, if you look at this, this has an equal number of left and right. So, the number of left is 2, number of right is also 2, but this is not balanced because I do not have a left parenthesis before my right parenthesis. So, this one gets matched with this one, that is fine, but now I have a right before a left. Okay. So, this is not balanced. Okay. Similarly, if I have something like, of course, this is also not balanced because I have 2 left and only 1 right. Okay. So, formally, the language is let us call it L3 is the set of all strings over these parentheses such that W is balanced. Okay. So, how do I write a grammar for this? So, firstly I should have that for every left I should have a right and the string in between is again balanced. Okay. So, basically a left gets matched with a right and it can nest another balanced parenthesis inside it, which is a smaller length, or it can be of the following form. Okay. So, I have some balanced parenthesis on the left and I have some on the right. Okay. So, if you look at this example, so here basically how do I generate the first string? Okay. So, if I want to generate the first string, so let us see this example. So, first I will replace S with an SS, okay, because I want to have this part and this part. Now, I replace the first S with left S right and I have the second S. Then I replace again the first S with left S right. Now, I replace the first S with epsilon. Okay, so, I need to add epsilon as well. So, I get left right S. Then I replace the only S with again left S right, and now I replace this with epsilon. So, I get left right left right, and you can show that any other balanced parenthesis can also be obtained by from this grammar. So, this is the grammar. Okay. So, now I will end by showing that regular languages are also context free. Okay. So, let So, let L be a regular language, which means that there is a DFA D, which is Q sigma delta Q naught F, that such that L is equal to L of T. So, from this DFA I will construct a grammar, okay, construct a CFG whose variables are, so let us call it V equal to R0 for every, or let us call it Ri for every Qi belonging to Q. So, for every state Qi I have a variable Ri. The terminals are the same as the terminals or the alphabet of D. So, it is the same set. The production rules I define as follows. If delta Q I A equals Q j, then add the rule Ri going to Arj, and if Qi is a accept state, then add the rule Qi going to epsilon as well. And the start variable is the variable corresponding to the start state, which is R0. Okay. So, this context free grammar accepts the same language as this DFA, okay, which shows that regular languages are a subset. I will not again go into the proof of why this accepts it correctly, but I will just stop with the construction. Okay. Thank you.